This is going to be a shorter video. Last time we established the basics of electric circuits. We derived the equation called Ohm's law, for example, that relates the voltage or potential difference across a resistor to the current through the resistor. Today we're going to start with a brief discussion about what a resistor or a light bulb does in a circuit. We talked about it a little bit last time around, but we'll go into it in a little bit more depth this time. And then we're going to talk about how do we analyze circuits in general using the concept of potential difference. Light bulbs are probably a little bit more obvious. When you plug in a light bulb into a circuit, it lights up. So what's happening there is that the light bulb is drawing energy from the battery in order to give off light. There's a conversion of energy happening. The battery stores electrical energy, and the light bulb is able to extract and use some of that energy and converts it into light. But if any of you have ever touched an incandescent bulb, you'll know that they don't just give off light, but they also radiate heat. And in fact, a typical incandescent light bulb gives off somewhere between 10 to 100 times more energy to heat as it does to light. So the light that you see from an incandescent bulb represents only a tiny fraction of the energy that the bulb is using. They're actually very efficient electrical heaters. That's why if you turn on a whole bunch of lights in a room, the room will actually warm up a little bit. You may have actually noticed that happening once in a while. It's also the principle behind the children's toy, like a bake light. It literally allows you to bake things, not very well, obviously, but it allows you to bake things by shining a light bulb on it. And that's just because an incandescent bulb releases much more energy in the forms of thermal energy or heat than it does in the form of light. So a light bulb is a device that uses electrical current to convert the electrical energy stored within a battery in order to give off light and generate heat. A resistor is very similar to a light bulb. In fact, a light bulb is often considered sort of a kind of resistor. A resistor accomplishes the same thing, except it just gives off the heat part of things. Resistors don't light up, they just warm up. If we were still in school, you would have already done several experiments with light bulbs and resistors in circuits by now. And one of the first things that students typically realize is that if you leave a light bulb or a resistor plugged in for a long time, and then you go to remove it, you'll notice that it's actually usually quite hot, sometimes almost painful to the touch. To understand why a resistor and a light bulb generate this heat, we have to think about what a resistor really is and what's actually happening in the circuit. A resistor is a part of our circuit that is not as good at conducting charge as the rest of our circuit. So if I have charges moving along my circuit, the ones that are being pushed through the resistor are going to have a harder time. There's more resistance to their motion. And the reason for that is if you, this is going to be very simplified, but if you zoom in to a resistor, like anything else, it will have atoms throughout it. In a good conductor, like in a piece of copper wire, something that allows charges to move very easily, the charge can move through and the atoms don't really interfere with the motion of the electrons as they pass through. The atoms are kind of invisible. The electrons are free to move kind of however they would like. But in a resistor, that's no longer quite the case. As the charges are moving through, once in a while, more often than in a conductor or a good conductor, the electrons will hit an atom and they'll end up kind of like scattering. And that results in sort of an obstacle to their motion. Instead of the electron going straight on through like it would in a good conductor, they end up bouncing around, constantly knocking into other atoms. And in fact, right, there's not just one electron going through here, there are a whole bunch. And so the electrons will also end up bouncing around and knocking into each other. We're not going to talk about the detailed, material reasons for why in some materials electrons can go through without being affected so much by the atoms, and in others, the atoms really get in the way. But that's really the distinction between what makes a resistor versus what makes a wire. Technically speaking, as we'll learn, wires have a little bit of resistance too. They're not completely, they don't allow complete free motion for electrons, but almost unimpeded motion. But again, if you think about it, the electrons are being pushed around in the circuit in the first place because of the battery. The battery has a potential difference. That potential difference creates an electric field, or is associated with an electric field. That field pushes charges through the circuit. So there's a field pushing the electrons in a particular direction through our circuit. And every time our electron hits something else, it's giving up some of the kinetic energy that it took from the battery. And it's being converted into, every time it hits an atom, the atom might start to jiggle a little bit. And each time it hits an atom, that atom is going to start to jiggle. And when one atom starts to jiggle, it can also end up causing the other atoms to jiggle. And if you recall from chemistry, temperature is simply the average kinetic energy of the particles in a system. So as our current passes through a resistor, the electrons that form the current are constantly hitting the atoms that make up the material, and that causes the atoms to start to vibrate and shake and everything, and that means that the object is starting to warm up. So what is happening is that these collisions are converting some of the energy from the battery into thermal energy of the material through the electrons. So the battery is giving kinetic energy to the electrons. The electrons are then losing some of that kinetic energy to the stationary atoms of the material. They start to vibrate and jiggle, which means the whole thing starts to heat up. That's what a resistor is. So what's the difference between a light bulb and a battery? Why do light bulbs light up and resistors not light up? They're really fundamentally kind of the same thing. Well, a light bulb is designed to reach really, really, really high temperatures, and that's why it lights up and a resistor doesn't. So a typical light bulb might reach something like 3 to 6,000 Kelvin, right? That's like the temperature of the surface of the sun. And specifically, it's the little metal wire filament that I showed in the previous video that reaches such high temperatures. If I were able to get a resistor to such high temperatures, it would also glow, just like a piece of really hot metal will start to glow. The difference is most resistors would be completely melted or otherwise destroyed by such high temperatures, but that's a topic for another day. So light bulbs are basically just resistors. Now, it is a little bit more complicated than that. When we talk about a resistor, if I say a resistor, I actually mean that it has a particular property. And that's that the resistance of a resistor, the degree to which it resists electrical current, is independent of its temperature. So as a resistor warms up, its resistance stays the same. That's a really nice property because oftentimes we want a circuit to have a consistent behavior, and that means as our resistor heats up, because that's what resistors do, its behavior in the circuit doesn't actually change. Light bulbs are different. The resistance of a light bulb does depend on the temperature. I'm not going to go into the details of how it does, but you're actually going to explore this a little bit in your next assignment. Some terminology that you should be aware of is that as a result of this temperature dependence, we often say that light bulbs are non-ohmic. And all that means is that their behavior is a little bit more complicated than Ohm's law by itself might suggest. Despite that, we will often use light bulbs in place of resistors because it's easier to talk about, this light bulb will be brighter, this light bulb will be dimmer, rather than what's going on with the resistor. And in those cases, we'll actually often ignore this temperature dependence. We'll assume that the temperature dependence doesn't really matter very much. It is worth knowing that they do in fact depend on temperature, and that also we will often ignore that fact. We can actually take all this and go even farther because we can quantify the rate at which these circuit elements are using electrical power. Let's say that our battery is providing a potential difference delta V, or a voltage delta V, and the resistance of our light bulb or resistor is R. We can use Ohm's law then to figure out how much current will be flowing through our circuit because we know the potential difference and we know the resistance. And so Ohm's law just tells us that I is equal to delta V over R. And power is equal to the work done over time. But the work done by an electric field can be written as the amount of charge being pushed across a potential difference, delta V. And so this gives us a relationship between the potential difference of the circuit and the charge that we're pushing through the circuit. But Q over T is just another way of writing the electrical current. And so this implies that the power dissipated by our resistor or our light bulb is equal to the current times the potential difference. So this is the rate at which energy is being used up by our light bulb or by our resistor, or in other words, the amount of energy being released by our resistor or our light bulb in the form of heat and or light is equal to the current through it times the potential difference across it. We can use Ohm's law to rewrite this in three different ways. I can get rid of delta V from this expression, and I can write this as I squared R, or I can start from over here and I can get rid of I can replace I by delta V over R, and I can also write this therefore as the potential difference squared divided by R. So there are three different ways that we can write down the power used by an electrical element in a circuit. And it's important to note that I is the current through the element using up the energy, and delta V is the potential difference across that element, and R is the resistance of that element. You'll see that we actually only need two of these pieces of information. If I have any two of I and delta V or R, I don't need the third, and the reason for that is because there's a relationship, Ohm's law, between the three of them. So if I know two of them, I actually do know the third one, which is why to express power, I only need to know two of them. Okay, so let's move on to more general properties of circuits, or rather how we go about analyzing circuits in general. So let's again stick with this really simple circuit where I've labeled four distinct points on the circuit A, B, C, and D. We'll use those labels to help us talk about what's going on here. What does it mean, though, for the battery to have a potential difference of what I labeled delta V bat for the battery? It means that the difference in value of electric potential at A to B is this. So, for example, if the potential at A is equal to 0, then the potential at point B is equal to delta V of the battery. The battery holds A and B at a specific potential difference. If, on the other hand, I said the potential value at A is equal to 10 volts, that means the potential at B is 10 volts plus delta V of the battery. So whatever the value assigned to one of these points is, the other one is fixed to be delta V apart. In this case, B is the positive terminal of our battery, or high terminal of the battery, so the potential will always be higher at point B than at point A. What is the potential difference between points B and C? To figure that out, we can use Ohm's law. The potential difference is equal to the current through that part of the circuit times the resistance of that part of the circuit. But there's no resistor between points B and C, which means there's no resistance between points B and C, because again, we're going to operate under the not quite accurate but good approximation that there is no resistance of bare wire. And so if R is 0, then delta V is 0, which means the value of potential at point C is equal to the value of potential at point B, because there's nothing but empty wire between them. If there's no resistance between them, then there's no energy lost between them, because there's no resistance to the current, so the charges will flow freely. And we can use the exact same process to argue that the value of potential at point D will be equal to the value of potential at point A, because once again, there is nothing but empty wire between them. There's no resistance to current. There's nothing to extract energy from our system. This is where it gets a little bit more fun. What about the potential difference between C and D? Well, we've already established that the potential at point D is equal to the potential at point A, and the potential at point C is equal to the potential at point B. And you'll notice that this is simply the opposite of the voltage across the battery. And so the electric potential difference from C to D across our resistor is equal to the negative of the potential difference from A to B, which is the voltage of our battery. So at point A, we have some value of potential. Then as we go through the battery from its low to high terminal, the value of the potential goes up. Then the potential doesn't change at all from B to C. Then it decreases from C to D as we go through the resistor. And then from D to A, it remains constant again because once again, we're going through nothing but wire. Note that the electric potential returns back to its original value. Or it doesn't really return because we're not going anywhere. This whole circuit exists at one moment of time. The electric potential at A has to have a single value. It can't have two values. That means when we started on our graph at point A and when we return to A, we have to end up with the same value in each case. So if I go clockwise through the circuit, I start at my potential at A. The potential difference increases across the battery because I'm going from the negative to the positive terminal. Then nothing happens along the wire. Then potential difference goes back down across our resistor, and it has to go back down by the same amount that it went up through the battery because the resistor turns out to be the only place there can be a potential difference because of Ohm's law. Ohm's law tells us that there will be no electric potential difference unless there is resistance through that part of our circuit. Note that in this circuit, the conventional current goes clockwise, and the potential difference across a resistor will always decrease in the direction of conventional current. And again, that's because conventional current goes from high to low potential, which means in this case, the left side, point C, must be higher potential than point D. You can think of it a little bit like a roller coaster, where the battery is what lifts you uphill, and anywhere there's just wire, it's just level track. And then the resistors are the parts where you fall back down, the terrifying parts. It actually is a pretty good analogy. Electric potential is analogous to altitude, basically, with gravity, so it really does work pretty well if this is something that helps you understand how it works. Batteries lift you up, resistors are what bring you back down. In your previous homework assignment, you already learned about the junction rule, which is that the current going into a given point on a circuit must be equal to all the current leaving that point. The analysis that we've just done with electric potential, though, gives us another rule. We call this one the loop rule. And it says that if you add up the voltages along an entire closed loop of a circuit, you always have to get zero. And that's because the voltage is how much the potential is changing. The battery increases the potential, the resistor decreases it, and in the end, when we return to the same part that we started, we have to have the same value. So when I add up all the changes, I have to end up with zero. Consider this new circuit on the left. This time we have two resistors. How is this going to change things? The junction and the loop rule, along with Ohm's law, basically tell us everything there is to know about this circuit. The junction rule tells us that the current is the same everywhere because there's only ever one branch. So at any given point, the current in has to be equal to the current out, which means the current flowing into one point has to be the same as the current flowing into the next point, and so on. The loop rule, meanwhile, tells us that the positive voltage across the battery plus the negative voltage across resistor R1 plus the negative voltage across resistor R2 is equal to 0. Note that the voltage across the resistors R1 and R2 are negative because I've elected to go around the loop of my circuit in the clockwise direction, and we established previously that the potential difference across a resistor is always going to be negative in the direction in which the current is flowing through the circuit. If I instead had elected to go the opposite way, which I could have said I'm going to go around my loop in the counterclockwise direction. In that case, I'm going backwards against the current through resistor R2 and R1, which means I'm actually going towards higher potential. So these would be positive quantities. And then I'm going backwards through the battery, which also means I'm going from the high terminal to the low terminal. So I would basically flip all of the signs in my loop. And so you can do it either way. but you have to be careful about which voltages are positive and which ones are negative. We can expand on this loop rule by applying Ohm's law. Ohm's law tells us the potential difference across a resistor in terms of the current flowing through it. So we can replace delta V1 and delta V2 with I1R1 and I2R2. But since the junction rule already told us that the current through each of the resistors must be equal to each other, we can simply replace I1 and I2 with just I. Note that we know the values of R1 and R2, they're given to us, and we know the voltage across the battery, it's given to us. So there's only one unknown left in this equation, the current through our circuit, and at this point, we can actually solve for what it is. Now that we have I, we can take this even farther. We can also use it to calculate delta V1 and delta V2. At this point, we can plug those values back into our loop rule, and we find that delta VB plus negative 1/3 delta VB plus negative 2/3 delta VB is in fact equal to 0, and so we can check our work to make sure we haven't made an algebraic or arithmetic mistake somewhere. Let's take a second and talk about these negative signs here for our voltages across the resistors R1 and R2. The negative sign in this case is indicative of the fact that we went around our loop in the clockwise direction, and so in the clockwise direction I do indeed go from high potential to low potential. But there's no reason why I can't ask what's the potential difference from the right side of R1 to the left side of R1, in which case it wouldn't be negative 1/3 delta VB, it would be positive 1/3. I'd be going from low to high. So generally speaking, if we're talking about what is the voltage across resistor R1 without any additional context, we would always give the positive number. The direction, the sign, whether it's plus or minus, would then be inserted afterwards by hand based off of whether or not you are choosing to go in the clockwise direction or counterclockwise direction, or rather, whether you're going in the direction of the current or in the opposite direction of the current. So this gives us our final tally. We've calculated the current through our circuit, and we've calculated the voltages across resistors R1 and R2. And that is everything that there is to learn about this particular circuit, other than power. We can actually learn a lot from this. One, we see that the current is smaller than it would have been if we removed either one of our resistors from our circuit. If I took out R2, the denominator here would be smaller. If I took out R1, the denominator would still be smaller. So by adding resistors in a row like this, we actually end up with a greater overall resistance of our circuit. We call this resistors in series. We say that resistors R1 and R2 in series because the current through R1 has nowhere to go but through the current R2. And in fact, it's not just R1 and R2 that are in series with each other. In this example, the battery is in series with them as well. There is only one branch of the circuit. There is only one current. That same current is forced to go through each element of our circuit in its entirety. And we can see again that by placing these resistors one after the other, we've essentially just added their resistances together. So when you have resistors in series, their combined resistance is simply the sum of their individual resistances. We call this combined resistance the equivalent resistance of those two. We call it the equivalent resistance because I could redraw the same exact circuit with the same battery, but instead of drawing two resistors R1 and R2, I could draw a single resistor with just the equivalent resistance of the two in series, and we would find the same exact current through our circuit. So replacing R1 and R2 with their combined equivalent resistance results in essentially the same circuit. This is actually pretty useful if you're building a circuit because you might not have access to an infinite number of different values of resistances. You might have to piece together the resistances that you want in your circuit based off of a finite number of options. By combining resistors in different ways, you can achieve different amounts of overall resistances for different currents flowing through your circuit. Finally, I want to talk about how can we actually measure these things? How can we measure voltage and current in an actual circuit? We call devices that measure current ammeters, named after the unit for current, ampere, and we call devices that measure voltage voltmeters. The circuit symbol for an ammeter is a little circle with an A in it, and likewise for the voltmeter, it's a little circle with a V. Consider this circuit again. let's say I want to measure the current going through this resistor. Well, because of the way ammeters work, you have to connect it to your circuit in such a way that the current that you're trying to measure has to pass through the ammeter. We just established that in order for that to happen, the ammeter needs to be connected in series with the resistor so that all the current from the resistor then passes through the ammeter. So where could I place this? There are actually a lot of places I couldn't put them. And in this case, because the current is the same anywhere in the circuit, I could place my ammeter here, or I could place it here, or I could place it really anywhere as long as it's kept in series, as long as I'm not adding another branch to my circuit. Voltmeters work a little bit differently. In theory, it's a little bit more complicated, and in practice, it's actually easier because you don't really have to disassemble a circuit in order to move a voltmeter around. For example, if I want to measure the potential difference across the resistor, I have to connect one end of my voltmeter to one side of the resistor, and the other end of my voltmeter to the other side. Because there's nothing but wire from this side of the resistor to this side of the voltmeter, the left side of the voltmeter has the same potential as the left side of the resistor. Likewise, there's nothing but wire between the right side of the voltmeter and the resistor. And so the right side of the voltmeter is at the same value of potential as the resistor. And so the potential difference across the voltmeter is fixed to be the same as the potential difference across the resistor over which it's attached. There's actually more freedom than this though, right? Because the potential at this point is the same as the potential anywhere along this open section of circuit. And so I could actually connect the right side of this voltmeter anywhere to the right side of the resistor until I reach the battery. Same with the left side. I could slide this around anywhere over here. So one of the things that means, for example, in this particular circuit is measuring the voltage across this particular resistor is not really different from measuring the voltage across our battery. But according to the loop rule, we kind of knew that already, because if there's only one resistor in our circuit, the voltage across the resistor has to be equal in magnitude to the voltage across the battery. And so whether I measure one or the other, I'll actually get the same answer. Here's where things get a little bit tricky. Let's say I now have two resistors. The ammeter is actually still pretty straightforward. There is only one branch of my circuit. The current in any one spot has to be the same as the current everywhere else because there's nowhere else for it to go but forwards. And so once again, I can actually place my ammeter basically anywhere I want, right where I already had it before. I could move it over here. I could move it even between the resistors or over here. Because the current has to be the same everywhere throughout this particular circuit, it doesn't matter where I measure the current. I'll always get the same result. It's a little bit more complicated again with the voltmeter. So for example, if I bring it back to where I had it before, we have several things to think about. One is, in order for it to still be true that the current through the rest of the circuit is unaffected, it means we shouldn't have any current through here, because if we did, the current through the battery would split. Some would go through this first resistor, some would go through the voltmeter, then they would recombine and both go through the second resistor, in which case the current through the two resistors wouldn't be equal anymore and our circuit would actually behave fundamentally differently. So we want to ensure that our voltmeter has the properties needed so that that doesn't happen. We want to make sure that no current passes through the voltmeter. Part of your next assignment is to figure out what property should the voltmeter have so that that's the case. The other thing is, what voltage is this voltmeter measuring now? Well, it's still measuring the difference in potential from one side of the first resistor to the other side of the first resistor. So it is in fact measuring the voltage across this top resistor. What is it not measuring? Well, it's not measuring the voltage across the second resistor. I could do that by placing a different voltmeter there. And now I'm measuring the voltage across the first resistor and the voltage across the second resistor. I'm still not measuring the voltage across the battery. Now there are two ways to approach this. One thing I could do is I could add these two voltages together and I should arrive at the voltage of my battery. The other thing I can do is I can place a third voltmeter across the ends of my battery. This also places a limitation on the properties of the ammeter. I still want to make sure that adding the ammeter and voltmeter to my circuit haven't changed my circuit in any material way. Just like we talked about with the voltmeters, we want to make sure that no current goes through them, otherwise it would ruin the consistency of the current through our resistors. But I also have to worry about what this ammeter is doing. If I put a third resistor here instead of an ammeter, it would change the resistance of the circuit and it would change the current through the circuit. So if I want to make sure that my ammeter doesn't affect the resistance of the circuit, I need to make sure that the ammeter has some specific properties. Again, that's one of the things I'm going to ask you to work out in your next assignment. So to summarize, ammeters measure the current passing through them. So if I want to measure the current through a resistor, I want to place the ammeter in series with the resistor because that will ensure that the current through the resistor is the same as the current through the ammeter. To measure the voltage across a resistor using a voltmeter, I have to attach the voltmeter differently. We call this kind of connection parallel. Parallel here doesn't just mean, oh yeah, they're drawn as like parallel lines, cool. No, that actually can get you into hot water. For example, I can have two resistors that are drawn parallel to each other, despite being in series with each other. And I can draw a resistor or two resistors in parallel with each other, despite sort of being drawn in line with each other. I think it's straightforward to see that these two resistors are not in series with each other. The current from the battery is going to be split two ways between them. So because they don't necessarily have the same current, the current isn't forced to go through one than the other. These are not in series with each other. So what makes them in parallel with each other? Well, two branches of a circuit are considered to be in parallel with each other if they're held at the same potential difference. So for example, in this diagram over here, because the end of the voltmeter is connected to the end of one end of the resistor by nothing but wire, and same on the other side, they have to have the same potential difference because potential difference through nothing but wire is zero, which means, again, the left side of the battery and the left side of the resistor and the left side of the voltmeter are the same, and the right side of the two are the same, and so the differences have to be the same. That's what it means for two branches to be in parallel, that the two branches of the circuit are fixed to be at equal values of potential difference. This is it for now. We will elaborate, we'll expand on these concepts of series and parallel later on, and in particular, we'll talk about the properties of circuits with multiple elements in parallel another time. So I will see you next time.